I'm going to start a basic introduction into our topic tonight, correlation and regression. Then we're going to pause to view a lecture, a recorded lecture on correlation and regression. Okay, that's down at the bottom of our page for session 12 for this session. Okay, it's got the PowerPoint as a PDF file and as a PowerPoint file, so you can follow along with it as you want. But I want to get started with an introduction before we go into that. Then when we're done with that viewing, when you guys online are viewing it on your own computers or here in the lab, we view it here. When we're done with that, we're going to come back and take a look at some examples of how to apply what we're learning about correlation or regression, how to use SPSS to define how closely correlated some variables are, when they're statistically significant, so on and so forth. But I think to start off with, what we're going to want to do is we're going to want to define or get a handle on what this idea of correlation is. Okay, so I'm going to get a piece of paper. Okay. So far, whoops. Let me get my pen working here. Okay, I think we're working now. Nope, not quite. Oops. Let me get organized here so that this thing's working. Try the other port. Hang on just a second. Oh, I'm going to have to do without this for now. I'll try and get it set up later on. I'm going to start off with let me open up a Word document then instead, so I can type some stuff. Okay, technology inevitably winds up failing at some point. Although we've been doing pretty good so far this semester. We managed to get all the videos to work, all the recordings to work, all the videos to work, so we haven't missed one of those yet. Keep my fingers crossed. Okay, so I'm going to ask you to imagine now what variables and what statistical tests and what variables have we worked with. Okay, so for starters, we learned about descriptive statistics. Okay, and in descriptive statistics, when we're working with categorical variables, for instance, names. We're working with, for instance, categorical variable might be hair color, for instance. Okay, we're working with categorical variables. We organize things as bar charts. We looked at frequencies, right? The number, we actually counted the number of people in each one of the groups, redheads, blondes, brunettes, and so on and so forth. So we organized data in that way. When we worked with numerical variables where descriptive statistics were concerned, well then we looked for patterns then when we organized that, right? For instance, instead of bar charts, we organized that in terms of histograms, right? So that there was a bar for each value, and the height of the bar represented the frequency of people within that range, not that particular name, but that range, unlike categorical variables. And in order to figure out where the middle of a numerical variable was, we worked with the mean, the median, the mode, and so on. Those were measures of the center of a numerical variable. Then we also were interested in how spread out those numbers were, that numerical variable was. In that case, we looked at range, we looked at interquartile range, we looked at percentiles, and most importantly, we looked at variance and standard deviation. I'm going to just put SD there so I don't turn the corner. Okay, so that's the way we work with descriptive statistics for categorical and numerical variables. Now, once we moved on from that, we wanted to be able to apply statistics to this, right? So for numerical variables, right, if we would breaking things up into groups, we might be interested in comparing means, for instance. For instance, comparing the mean alcohol level of American beers to German beers, comparing the mean blood pressure for people who exercise versus people who do not exercise. In other words, we'd be combining a categorical or nominal variable with a numerical variable. Okay, and we'd be interested in seeing if there's a difference in the mean between the categories. And sometimes we were comparing the mean to a specific value, say a blood pressure of 100, right, versus the mean not being above blood pressure of 100. Okay, and we use the kind of test that we used to demonstrate that was called a t-test, right? That's a single sample t-test because we're comparing the mean that we're trying to examine to a specific value, not to a mean of a different group. Well, then on the other hand, we wound up in situations where we're comparing the means of two groups. The mean of group one, whoops, one to the mean of group two. That the word's going to fight me on this. Okay, that's a t-test also, except that t-test is for independent values. Variables, right? Those are independent and randomly selected, right? So we'd be comparing the means of those things. And our alternative hypothesis there would be mu1 does not equal mu2. Okay, so we compare the means of two groups if we wanted to see if, say, a drug was working, if we want to see one group had a higher blood pressure than another group had a higher blood lead level, higher blood sugar level, so on and so forth. Well, on occasion, we might be looking at means in numerical values, the middle of the range of numerical values for more than two groups. Mu1 equals, as our null hypothesis, equals mu2, whoops, equals mu2, equals mu3, equals mu3, equals mu4, and so on and so forth, up to whatever number of values that our categorical variable might have. Okay, mu n, let's say. Okay, so for that situation, we use, remember what test we used? We used analysis of variance. And we actually ran that in two ways. First, we ran analysis of variance to find out if any of these means were different from one another. Our alternative hypothesis would be that at least two of these means are different, right? If we can reject our null hypothesis, accept our alternative hypothesis, we would then run post hoc tests. To determine which of these means are different from one another. If we fail to reject our null hypothesis that the means are all different, means are all the same, then we wouldn't run our post hoc test. We wouldn't go any further than just running analysis of variance. Okay, so we also learned about confidence intervals and so on and so forth. One of the things, then we spent some time with crosstabs. or contingency tables. And to evaluate whether there was an association between two categorical variables, for instance, diabetic or not diabetic, and let's say elderly or not elderly, right? Each one of those is a category, right? Two categorical variables or three different values of categorical variables and so on. When we were comparing categorical variables together to see if there's an association, we used a number of tests. We used chi-square, we used the odds ratio, and we used relative risk. Okay, so what do we have here? We have a way to work with categorical and numerical variables, right? That was our t-tests. We have a way to work with multiple values for categorical versus numerical variables. We had a way to work with categorical versus categorical variables, right? Well, the one thing we're missing is how do we show an association or no association between two numerical variables? How do we show that association? Okay, well, what would an association like that look like? Let me give you an example. Let's say you want to analyze the amount of fire damage that occurs at fires in New York City and the amount of firemen that respond to those fires. Okay, so let me think about this. Those are two categorical variables, two numerical variables. One numerical variable is just simply the number of firemen that respond, right? Number of firemen, right? And that might be 2, it might be 4, it might be 23, it might be 100 in a really big fire. The other numerical variable is the cost of damage that occurs at the fire. Okay, and that might be $1,000, it might be $10,000, it might be $1 million, right? Could be a number of different values, but those are all numbers. Okay, so each one of these different numbers of firemen is associated with the amount of cost that occurred, the damage that occurred at that particular fire. Now I'm going to ask you a question. Do you think that there's an association between the number of firemen that respond to a fire and the amount of damage that's done at that fire? Well, you guys tell me. What do you think? Yeah, it could be, right? It makes sense, wouldn't it? Well, okay, it makes sense. Now, let me ask you this. Do you think the firemen are the ones causing the damage? Is that damage occurring because of the firemen? Right, exactly. I agree with you guys 1,000%. In other words, it seems what's likely happening there is that there's an association between the number of responders. Okay, where's my number of firemen that respond, and the damage, dollar value of the damage that occurred at that fire. And it's because if you have a big fire, you got a lot of firemen responding to it. You get a small fire, you have a small number of firemen responding to it. This is an example of a correlation, an association. We use a special word for this. It's really an association between two numerical variables, the number of firemen and the number of dollars that the fire cost. There's an association between two numerical variables, the number of firemen and the dollar value of the damage. That association we give a special name, a correlation. We give it that name because it's an association between two numerical variables. Now, I could actually draw a graph if I wanted to. If my tablet were working right now, I would actually maybe try and sketch out a graph. But imagine this. I could draw a graph where I could have the x-axis be the number of firemen and the y-axis be the amount of damage. So that for each value, for instance, 2 firemen show up and there's $1,000 worth of damage. 4 show up and there's 10,000. 23 show up and there's $1 million worth of damage. I could draw a graph where the y-axis is the cost, the x-axis is the number of firemen, and each one of these instances of a fire represents the coordinates, the XY coordinates. 2 firemen and $1,000. 4 firemen and $10,000. 23 firemen and $1 million, right? I could actually draw a point for each one of these X and Y axis and look and see if as the number of firemen goes up, the cost goes up. I could even, if it looks linear, I could even try and draw a straight line to try and see if you could draw a straight line between them. Okay, so this is there's an important distinction between correlation and causality. When you look at correlation, all you're interested in is the fact that there's an association between these two numerical variables. You don't care about causation, right? Correlation just looks at the association. When we get into talking about regression, which we're going to, after the video, we'll get into actually, you'll hear about the regression on the video, and after we get through the video, we'll actually be performing some operations that we call regression, but we're not going to worry about them right now. Okay, the important thing is we understand correlation does not necessarily mean causation. Okay, however, we can because we can work with these numbers, we can take a look at whether or not this association maybe mathematically is thus due to chance, or if it looks like statistically that there really is an association. So for instance, what we might be interested in saying is, for a null hypothesis, is that there's no association between the number of firemen and the amount of dollar damage. And there's an alternative hypothesis. We might say that there is an association, right? So we want to know whether or not the data we're looking at can actually justify rejecting this null hypothesis and accepting the alternative hypothesis. And for all fires in the United States, being able to say that there really is an association with less than 5% chance of being wrong based on the data that we're working with, right? So now the only thing is that it's pretty sloppy. Just there's no association. There is an association. We can actually quantify this, and we're going to take a look at a value that we're going to call Pearson's correlation coefficient. I probably won't talk much about Pearson, but I'll keep his name on it for the time being. And that's symbolized by the character R. And that Pearson's correlation coefficient, lowercase r, except that this is going to fight me to give you, yeah, I don't know why it does that. I think you can turn that off. That value R can have a number of, can have a range of values. It can have a value from minus one through 0 to +1. The significance of that is if that R is equal to 0, right, there's no correlation. It's just random. The numbers have no association between them, right? So, but the closer the numbers get to 1 or -1, the stronger the association is. So we can use this two ways. We can calculate this coefficient called R. And the closer it is to 1, the stronger the correlation is. The stronger the association between these two numerical variables is. Okay, now you could have a positive one or a negative one. Anybody want to hazard as a guess as to what the difference between having a correlation of +1 versus -1 might mean? Well, for instance, I have a situation here where a positive relation versus a negative. Yeah, that's good. That's good, Ange. I have a situation here where the number of as the number of firemen goes up, the cost goes up. That's a positive association, right? On the other hand, I might be looking at two numerical variables. One might be the percentage of the people in a state that are vaccinated against the flu versus the rate, the prevalence of flu in that state. And in that situation, as the percentage of people who are vaccinated goes up, the percentage of people who get the flu goes down, right? So that's a negative correlation. If I were to draw it as a line, which I will later on, if I would draw it as a line, that line would be sloping up for the firemen and sloping down for our association between flu vaccine and number of cases of flu that we wind up with in a state, right? So that's a negative correlation versus a positive correlation. Well, what would I use now instead of this kind of sloppy description, association, no association? Since we're going to use R to define whether or not there's a correlation, how strong it is, well, what I might say is that my null hypothesis, right? And don't worry about this if it doesn't make too much sense now, because it'll be a lot clearer once we start working with real numbers. My null hypothesis is that R is equal to 0. And what does R mean? Equal to 0 mean? It means there's no association, right? Just random. Okay, and what's our alternative hypothesis? Right? R does not equal 0, exactly. R does not equal 0. And that means that there is an association between these two variables. Now, the real key here is that how can I prove whether or not I can reject that null hypothesis and accept our alternative hypothesis? But it's interesting in this case, a little bit different than some of the other stuff we've done. Not only does this null and alternative hypothesis tell us whether there really is not an association and whether or not you can reject it, but it also, that R value also separately implies the strength of the association. Right? So in other words, I could have an R value of R is equal to, I could calculate an R value equals R value, imagine that's a lowercase. I could calculate an R value is equal to 0.68. Looks like a pretty strong association. But you know, when I calculate my p-value, my probability of being wrong if I reject my null hypothesis, maybe it comes out to 8%, 0.08. Well, you know, maybe I just don't have enough, even though I calculated the association to be pretty strong, maybe I don't have enough data points to be sure that that association is not due to chance. So in this situation, it looks like a pretty strong association because it's close to 1, right? But I don't have enough data to say that it's not 0, right? I just can't justify rejecting the null hypothesis that says it could be 0. Okay, so sometimes you might wind up with a correlation of 0.1, right? Which is a very small association between two things, but that might be, we might have enough data to show that that's a real association. In other words, there's a lot of variability, but that association really exists, right? So one of them, this R value gives us how strong the association is, and the p-value, the probability, the significance, tells you whether or not you can reject the null hypothesis, that you have enough evidence to say that it's not 0, that there really is a true association. We'll work with that in just a little bit. Okay, so just to give you an idea, just to get some interesting looks at maybe situations where you get some association between correlation and causality, I'm just going to pop open a quick website or two. Okay, and I'm going to go here. There's a link to this. Just a coincidence. This fella is a statistician, and his hobby is to put together, I'll accept, I guess. I'm sure I'll get some ads as a consequence of this. He puts together, examines many different associations that there's clearly no causality, but for some reason, there seems to be some sort of association between them. Correlation, not causality. The more people that eat cheese, the more people are killed by their bed sheets. Now, he demonstrates that. He doesn't use the correlation coefficient. He uses values that he uses techniques where he's showing it graphically. I'm gonna see if I can't get this to go away by answering this question. Okay, good. So there you go. Let's see if he's got a couple of others here. The age of Miss America correlates with murders by steam, hot vapors, and hot objects. Well, I mean, if you look at that chart, boy, it looks like there's quite an association between the two of these. Okay, per capita consumption of cheese, number of people tangled in their bed sheets. Let's see what we got here. What else we got here? Well, I have it. I think I have another link there. Obviously, he does this to grab views and advertising and so on and so forth. So he's got a sucker in me because I find this pretty interesting. Let me see if I can't get back to our links and open up another one here. Here we go. This is the main page too. It's called Spurious Correlations. Suicides by hanging, strangulation, and suffocation, and the amount that the U.S. spends on space science over this period of a decade. Pretty strong association there. Number of people who drowned by falling into a pool correlates with the films Nicolas Cage appeared in. Number of people died, so on and so forth. We saw that one. Per capita consumption of margin is related to the divorce rate in Maine. Now, I don't think personally that there's any real causation going on here, but it certainly is. It gives you an idea that on occasion you're going to see things that suggest that there's an association, but there's something else going on below the surface that you may be able to discern, or maybe not. Maybe you'll never be able to figure out why there's this spurious correlation between these seemingly completely unrelated things. Okay, so you have the link for that if you want to play around with that and see if it's pretty interesting. And see if it's interesting to you. Right, inversely. I'm looking at your comments, and a lot of them are right on the button in terms of correlation. So, okay, let me get this out of the way. So, I am going to open up a file. Let's see if I can find it. Now, okay. I'll tell you what, let me download it fresh. I'm sure I'm working with the same file that you guys have on Blackboard. Okay, I'm going to pull down this file called age versus blood sugar.sav. Well, actually, before that, I'm going to work with another one. I'm going to pull down this file called pizza versus subway fare.sav. Okay, and I'm going to save that to my desktop. Okay, let me get this back out of the way. And let me move this, clear things up here a little bit so I can get some space to work with. Okay, I'm going to open SPSS. And I'm going to import the data that I have in that file into SPSS. And here's our pizza versus subway fare. Let's take a look at what this data represents. Well, I have three variables. I have the year, I have pizza, the cost of a slice of pizza, and I have the cost of subway fare. Right, so I'm going to go back here to variable view, and I'm going to examine this a little more closely. And I notice that the year is a categorical variable. It is, because it's not really numerical. I'm not going to find an average year. I'm not going to average the years, 1999 to 2009. They just indicate a period, a specific sample, a point when I took a reading, right? So that's a nominal variable. But then I have two numerical variables. One is the cost of a slice of pizza, right, which I call pizza here, and the other one is a subway fare, average subway fare for that year. So let's go back to the data view. So this suggests that in 1960, the subway fare was 15 cents. I can attest to that because I was about 10 years old, 10 or 11 years old then, and I would take the subway to Coney Island every once in a while without my parents knowing about it, and it would cost me 15 cents. They actually had a token, a little tiny token, which you had to buy because the machines were calibrated for this one coin. And believe it or not, pizza costs about that same thing as a subway token. Let's see, around here, sometimes it varied a little bit, wasn't quite the same, but man, it looks like there's an association between the cost of pizza and the cost of a subway fare. how can I demonstrate that graphically? Well, you remember when I mentioned that like we could perhaps see an association between two numerical variables by graphing them together, using one as the x-axis, the other as the y-axis. So we have each year, each subject, each person, each year, for instance, in this case, represents a value, a point on that graph. So this would be the x-coordinate, and this would be the y-coordinate. This would be the x-coordinate, the y-coordinate for points on a graph. So I'm gonna try and graph that. I'm going to go up to graphs. I'm going to go to legacy dialogues because it's just simply the simplest and quickest. I'm going to go down to scatter dot. That's what I'm going to choose. And I'm going to say simple scatter dot. And what it's going to do, it's going to allow me to input a variable for the x-axis and for the y-axis, and it's going to plot each point, each associated point on an xy axis. Okay, so I'm going to put the cost of a slice of pizza. Notice I'm not year, that's a categorical variable, right? The cost of a slice of pizza, I'm going to put into the y-axis, and the subway fare, I'm going to put into the x-axis. I'm going to say, okay, and it'll graph it for me. So each one of these values now is going to show up as a point here. So the first one I showed you, 15 cents and 15 cents is the cost of subway fare and the cost of a slice of pizza. Okay, so it sure looks. Would you guys say that there's an association between a subway fare and the cost of a slice of pizza? Sure looks like it, right? Okay, and you know, I looked some of these numbers up. The other ones I made up just based on kind of memory, right? Am I wrong about what a slice of pizza nowadays is about $2.75, right? Yeah, well, yeah, you got the dollar pizza, but I would not personally call that stuff pizza, you know. But I mean, for the most part, it's about $2.75 per freezers, okay, for a slice of pizza, right? So and the subway fare now is about, what is it, 245 or two? It's 275. I guess whether or not you're using the card, how you use the card and stuff like. Yeah, it's around the same, right? And historically, in New York City, it's been going up and down like that. It's almost like it's fixed, right? So I'm gonna take a closer look at this by seeing, is this really this it looks almost like a straight line. Is this a linear relationship? So I can actually double click on here, open this graph in a new window, an editing window, and I can go in here from the editing window. I can change the font, I can do a whole bunch of other things, change colors and so on. Uh, uh, One of the things I can do is I can ask SPSS to fit a line, a best fit line to this data that's here. And I'm going to say, okay, it does it automatically. And let's see what I have wind up with here. Well, if you look at this, and actually I can close this now, it'll be transferred to the graph below. Oops, there it is. Okay, let's see if I can look at this. Well, look at this. There's a few values that are off, but there's a very good correlation here, it seems like. Doesn't it seem that way, right? So sometimes it's right on the money, but often it's just off a little bit, right? There are some values that it misses. But this line gives me an idea of what this relationship looks like. It quantifies the relationship for me. I'm going to do this another way just to show you that. I'm going to go to graphs, legacy dialogues, scatter dot. I'm going to go to simple scatter dot again. Okay, it should still have the variables in there. I'm going to reverse these. Subway, whoops, cost of a slice of pizza. I'm going to put one in the x-axis, one in the y-axis. Okay, I'm going to do it again. And sure, it looks a little bit different, doesn't it? But it still gives me that kind of linear relationship, right? So, well, what does that tell me about this so far? Well, you know, it doesn't matter when we're looking at correlation. It doesn't matter which one you make the x-axis and which one you make the y-axis. Now, moving forward, when we get into regression, when we're looking at regression, we're not only going to be satisfied, we're not going to be satisfied with just showing an association. We're going to want to quantify that association. Not only that, but we're going to want to examine whether there's some causality involved. For instance, we're going to want to know which one is the independent variable and which is the dependent variable. Which one drives the other? So for instance, If I were to ask you the rate of state by state, you have 50 states, the rate of lung cancer in a state versus the rate of smoking in a state, right? So it seems to me that states that have a lower rate of smokers, lower percentage of smokers, going to have a lower lung cancer rate, right? So let's say that there's an association there, and I have 50 points for the rates of lung cancer, 29 cases per 100,000, 50 cases, and average percentage of smokers, 10%, 14%, 22%, so on and so forth, in different states. Now, would you expect that to be a positive correlation or a negative correlation? Positive, right? As the number of smokers goes up, number of percentage of lung cancers goes up as well in each one of the different states. Okay, now if I were to ask you, is it causative? What do you think? In this case, there's a good shot it is, right? Unlike the firemen, smoking does have an impact on the rate of lung cancer, right? In fact, it's the primary cause of lung cancer in the United States. There's other causes. Anybody, we don't have any OHS majors here. Anybody know what the second largest cause of lung cancer in the United States is? Asbestos is a good guess, but asbestos is limited to people who have significant exposures to it, right? That really increases the rate, right? The second largest is nope, not not secondhand smoke. Keep guessing, right? How many guys live in anybody here live in northern New Jersey or Pennsylvania? Nope, nobody. Okay. Anybody here ever heard of something called the Redding Prong? The Redding Pond is a geological structure. It runs through Pennsylvania, northern New Jersey, and up into New England. It's a geological formation that has when I say has an unusually large amount, I mean it has a trace amount, but more than areas that don't have any amount of radium and uranium in the soil. And that radium, over time, slowly decays into a gas called radon. And radon gets into people's basements. As you guys know, it seeps into buildings and so on and so forth, particularly residential buildings and basements. And radon is the second largest cause of lung cancer in the United States after smoking, right? So keep that in mind the next time that you go and like want to buy a house or something like that in the areas, in the geographical areas where these kind of deposits exist. Okay, in case you don't believe me, let me just check that. I want to know if that, the statistic comes from a while ago, but let me just check that. Keep in mind, smoking by far is the first. Let's see. Oh boy, why isn't that starting up? I have. Should have not even bothered starting. I already have this open. You get a new window here. Okay, radon, lung cancer rates. Know the numbers. See if they have the causes listed in order. Let me try this one other way. List of lung cancer causes. Causes of lung cancer. Oh, if you want to check that statistic, if I'm wrong, I want to stop using it. Try this one more time. Causes, leading causes of lung cancer. Let me put in a couple that I know are smoking, radon. Try and pin down the actual list. First, I got the ads. Wait a bit. Smoking, Is rating on the leading cause of death? The answer is radon and cancer. Population. How many people? Cigarette smoking is the most common cause of lung cancer. Radon represents a far smaller risk for this, but is the second leading cause of lung cancer in the United States. Estimates that 15,000 to 22,000 lung cancer deaths in the United States each year are related to radon. Okay, so I'm not wrong, right? So pretty interesting statistic, right? So a lot of these dangers, exposures, and so on and so forth that you read about constantly in the newspaper and so on and so forth, mold and so on and so forth. A lot of this is driven by whatever happens to be kind of the most popular piece of information that just recently got released. But in the meantime, here's a real hazard that many, many people are exposed to, and most people don't really even recognize the degree of the hazard. It just doesn't seem to grab public attention quite as much. Okay, so at any rate, so I was talking about smoking and so on and so forth. So in that case, that we can say that smoking and lung cancer cases, the percentage of smokers and the rate of lung cancer in each state, that is an association that's causative. The smoking is the leading cause of cancer, and we would expect that the smoking is actually causing the increased rate of smokers is actually causing that. So one of those numerical variables is going to be the dependent variable, and the other one is going to be the independent variable. The independent variable is the one that causes the change in the other one. The dependent variable is changed by the independent variable, is dependent on what the value of the independent variable. So which one's the independent variable or the causer? Smoking, right? Smoking is the causer. And which one is the dependent variable? The rate of cancer, right? Exactly right. So, if I were working in that situation, when I were putting together my first look, very frequently my first look for an association is to produce a scatter dot, just so I can see visually what it looks like. In that case, when I'm defining my axes, then in most cases, what I'm interested in doing is I would put my independent variable, smoking percentage, into the x-axis, and my dependent variable, the rate of lung cancers, into the y-axis. In that case, I would not reverse these. I would always use the x-axis for my independent variable, the rate of smoking in this particular case. Okay, so what I'd like to do now, we're going to come back and we're going to play with this some more. I'm just going one more thing just to show you something. I'm going to go down here and show you that there is a place down here for these tests, regression and correlation. Correlation, bivariate means two variables, right? Two numerical variables. That's what we're working with here. And the way that I tell it which variables I'm working with is I just simply move them into my variables box. Notice I can't click OK here because I only have one numerical variable in there. I click on the second one. Now I can click on OK. I have a few options in here. We're not going to be too concerned about this right now, but I can just go ahead. I'm looking for a Pearson's chi-square. You're always going to do two-tailed test here. Then you're going to click OK. I'm sorry, Pearson's correlation coefficient. And here's my Pearson's correlation coefficient, also called R, right? My Pearson's correlation coefficient is 0.993. Well, it's a positive number. That means there's a positive association between the cost of a Subway token and the cost of pizza, right? And it's a very strong correlation. Well, remember that in order for me to make sure that this is a statistically significant one, that it really isn't zero, and I just happen to get unlucky and get the wrong numbers, right? Well, I go down to my significance, the probability I'll be wrong if I reject my null hypothesis, and that is less than 0.05. So not only is this a very strong association and a positive one, positive number means that they're positively associated. As one goes up, the other goes up, and the significance is 0.05. Now, I'm okay with this on correlation because I'm not making any predictions about causality. I don't know. I don't see any reason why the cost of a slice of pizza might make the subway fare to change, just like I don't see why the cost of the subway might make the cost of a slice of pizza change. There's other things going on in the economic world that raises the price of both of them at the same time, apparently. It just happens that these psychologically seem to be very strongly associated. So that's our Pearson's correlation. That value, that 0.993, you won't see too many like quite as good as this. Remember, this is kind of fabricated data, right? You won't see too many like this. That number represents the strength of the association, whether it's positive or negative, right? In the meantime, notice how it does it both ways. It compares the cost of a slice of pizza, right, to the cost of a slice of pizza. Well, it's the same thing, so the correlation is 1. It's perfect. Cost of a slice of pizza to the subway fare, well, it's a very strong association. Then at the bottom, as SPSSs want to do, it actually just turns the variables around, says subway fare versus the cost of a slice of pizza. We wind up obviously with the same thing. It's the same comparison. Don't let SPSS throw you off by the fact that it happens to do that exact analysis twice. Okay, but that's our R value that we wind up, our Pearson's correlation, and this is our probability of being wrong if we reject the null hypothesis. That would be R is equal to 0, correlation is equal to 0. So this tells us if we can reject our null hypothesis. Okay, so let's take a break now from this. I'll put the recording on pause and screen on pause, and what I'd like you to do is I would like you to play this hour and 19-minute long lecture by Levi. Okay, and we'll come back to work on this again. So let's say that we're going to meet back here at roughly 7:30. Okay, if you don't get through all of it, or if you take a break on it and stuff like that, go ahead and you can always listen to the rest of it later. Okay, so you guys go ahead. I'll pause the recording, and we will get back together here at 7:30. Okay. Resume, and we're recording again. Okay, so as I said, I'm going right now to Blackboard, to our current session, and I'm going to download a data file that we're going to work with. So you guys might want to download that also. Okay, and let's go down here and get age versus blood sugar. Right click on it, save it on my desktop. Then I'm going to go over to SPSS, which I happen to already have it open. I'm going to say open data, and here is my age versus blood sugar. SPSS is going to open this database, and I see I got 2 variables this time. I have age and blood sugar. So each one of these lines, each one of these rows represents an individual, represents a subject in a study. We measured their age and we measured their blood sugar. Okay, and you might say that blood sugar levels, fasting blood sugar levels might be higher in people that are more likely to be diabetic, and perhaps as people get older, they're more likely to be diabetic or have issues with insulin sensitivity. So we might see among older people higher levels of blood sugar. So I want to examine this idea. Is there an association between age, a person's age, and their fasting blood sugar level? Okay, so let me look at my variable view, make sure these are both numerical variables, scalar variables. One represents age. I didn't bother to put a label in there. The other represents blood sugar. I just put a label in there so that the tables have that space between blood and sugar, make it look a little bit more normal. Okay, so what's the first thing I might want to look at here to see if there's any relationship here at all, right? Just to get a visual impact of, is there a linear relationship between these things? What do you guys think? What did we do before? Well, we're going to graph it, right? Graph, legacy dialog, scatter dot. Okay, so I'm going to click on scatter dot and say define. And now, unlike correlation, since I know I'm at some point going to want to see if there's a relationship, a causal relationship between age and blood sugar, I'm going to make sure I put my independent variable in the x-axis and my dependent variable in the y-axis. The independent variable is the causer, the variable that causes the other variable to change, and the y-axis is the dependent variable, the one that is dependent on the variable, the independent variable. So what am I going to put into age, into x-axis? I'm going to put age in there. Okay, and into the y-axis, I'm going to put blood sugar. Okay, so I'm going to go ahead and take a look at what this looks like. And let's see if it looks like I have a linear relationship here. Well, it does appear that as a person's age goes up, it appears that their blood sugar level goes up also. It's not just a kind of like a blob here in the middle where there's no association between age and blood sugar. It's not the straightest line, but it does look like it's linear, and it does look like it moves upwards. I'm going to double click on here and get it to draw me that best fit line again. Okay, there's that best fit line. Okay, let's take a look at that line. Okay, so now I want to calculate, I want to describe how well this line fits all of these various values that are here. This particular person was about 38 years old and almost perfectly falls on the line that we drew here. This person is very close to this person, but this person is, there's quite a bit of an error here. And look, the error looks fairly random, right? It's kind of randomly distributed here. There's some error here, but the line seems to represent roughly how blood sugar goes up with age. Okay, so now in order to understand whether this is statistically significant, in other words, whether this association is real statistically, in other words, I can reject our null hypothesis, I'm going to have to do a correlation. I'm going to have to calculate a correlation coefficient. So I'm going to go here to analyze. I'm going to go down to correlation. And from correlation, I'm going to go to bivariate. So I have age, right? And I have blood sugar. Now, since I'm only looking for a correlation, just to see if there's a correlation, calculate Pearson's correlation. Okay, I'm just going to move those two in there. I don't care which one I move in first. So we're not looking at causality, just is there an association that's not due to chance. So our starting point here is, what's our null hypothesis here for our correlation? Our null hypothesis is that there is no association, which would mean that the correlation coefficient is equal to 0. So R is equal to 0 is our null hypothesis. Now, one of the things that came up in the lecture, right, is that really when we're describing a null hypothesis, when we're working with means, we describe it as mu. We're examining the means of the entire population. We're using the Greek letter in our null hypothesis. We should do the same thing here, right? So our null hypothesis, instead of saying R is equal to 0, let's say rho, R, Greek letter equivalent R is equal to 0. That's saying that the population coefficient for everybody is equal to 0, not just the R value, which represents the correlation coefficient for our sample of 10 people. Okay, R represents our correlation for 10 people, rho represents for the entire population. And we're really trying to use our sample to prove that the entire population correlation coefficient is significant and that this association is real. Okay, so I'm going to put both of these in there, and I'm going to calculate my Pearson's correlation coefficient. Okay, let's see what it comes out to. It comes out to, let's see, Pearson correlation, age versus blood sugar is 0.821. So right off the bat, let's examine this. Is this a good correlation? Is this statistically significant? In other words, can I reject a null hypothesis that rho is equal to 0? That the correlation coefficient is not equal to 0, so therefore there is a real association between these two. That one of these, as one changes, the other changes as well. And thirdly, is it going to be a positive correlation or a negative correlation? Okay, so let's start in the beginning. Is this a positive correlation or a negative correlation? Positive. As age goes up, blood sugar goes up. Is this a strong correlation or a weak correlation? Strong correlation. It's close to one. It's very strong correlation, as a matter of fact. And is this a statistically significant correlation? Can I reject the null hypothesis that rho is equal to 0? I can, because my significance, my two-tailed significance, my p-value is less than 0.05. I can reject this and be better than 95% certain, or no, with less than 5% chance of being wrong, I can reject my null hypothesis that rho is equal to 0. In other words, that there's no association between these two variables. So right off the bat, I've learned something about these variables. I visually looked at how they are associated, and I've also numerically shown that there is a positive real correlation between these, at least within the limits of our statistical test. Okay, well, that's pretty interesting. The only problem with that is that now now that we know that, how can we apply that? Well, if you go to a doctor's office, how does he know what your age is? You ask him. He asks you, right? You just tell him what your age is. But how does he know what your blood sugar is? He has to test it and send it out to a lab, right? Doesn't do it right there. Sends it out to a lab. In fact, some blood tests have to be are challenge tests where it's actually a fairly intrusive, expensive test, time-consuming test, right? But normal blood sugar, yes, at a minimum, has to take a blood sample and send it out to a lab, and then he has to deal with handling blood, having a lab pick samples up, having a license to handle blood, bodily fluids that might be contaminated, and so on and so forth. So there's a lot to hiring a technician that knows how to take blood samples and so on. And then the occasional patient that faints when he takes the blood sample, and he has to deal with them too. So it'd be really nice if we could ask a person's age and predict what his blood sugar would be just from his age. Well, you and I know that's not going to be a really practical way of doing this, because our the importance of understanding what his blood sugar really is, we're not going to risk just guessing at it based on his age. Let's make believe for a moment. Let's make believe for a moment that maybe this will work for us. Maybe this will work well enough for us that we don't have to send out blood samples anymore. At least not on a first visit, for instance. Okay, so let's see if there's a correlation here. So I'm going to say analyze. We saw a correlation. Now I'm going to perform a regression. Analyze, and we'll see what the differences are here. Analyze regression, linear regression, right? All these analyses we're talking about here assume a linear relationships. That's one of the reasons why it was so important to create that scatter plot, because that's your first look at whether indeed the relationship is truly linear, right? If it lays out like a straight line. Okay, so now this time, notice there isn't a single box, there are two boxes here. It requires us to identify which is the independent variable and which is the dependent variable. So I'm going to take age, and I'm going to say to myself, well, that's the independent variable. That's going to be the determining variable. And what's going to be the one that's going to be dependent on that determining variable? It's going to be blood sugar. I'm going to put that into the dependence variable. I'm not going to worry about methods and so on. I'll leave it method enter. We'll worry about that. So it may be in our next class. And I'll click OK. Let's see what winds up happening here. Well, we wind up with a number of tests here. The first test model that we get, a test that we get, is it recalculates the value of R for us. The value of R is 0.821. It does exactly the same thing that we calculated when we did the correlation coefficient. And you might have noticed that that was based on the variability of the individual subjects with relation to the average value for blood sugar and age for X and Y and so on and so forth, and the standard deviation over the standard deviations. and that gave us a proportion, this proportion called R. You're not going to have to worry about, for our class, you're going to have to worry about how that R was calculated beyond the kind of description that you got in the lecture. Don't worry about that beyond that, okay? But we know what that means. That means it's a positive correlation. It looks like a good, strong one. Now, let's take a look at this R squared. Now, R squared is just simply R, the value for R for our sample, squared, multiplied by itself, and it comes out to be 0.674. Anybody remember something interesting that he told us about R squared? In addition to calculating it by just multiplying R times itself to get R squared, what other way do you have that you can calculate what R is? Anybody remember what that is? It's a ratio of the variability in predicting the y value from x. It's a ratio of the variability of what you would get for your value for y, right? Based on the amount of the error that's random, the error the error that you would predict versus the ratio of that error and the total variability of those values of y. So this is the percentage of the variability between X and Y, between age and blood sugar, that can be attributed to age. In other words, we can say that 67% of the variability in blood sugar can be attributed to age. Another way of saying it, the 67% of the value of blood sugar is explained by a person's age. Well, what does that imply? That implies that 33% is explained by other variables or just by chance instead, right? But that's pretty good. That single thing is that good a predictor, right? Now, these numbers are of course all made up. I doubt if it's going to be anywhere near this, but that's the idea here. That R squared quantifies for us how good a predictor that this model that we're about to put together makes. So R squared is important to us. That's good. Okay. So now let's go down here to our significance. Remember when we did R squared, when we calculated R, remember what our p-value was? It was 0.004. This is evidence that this relationship is not due to chance, right? So in other words, that we can reject our null hypothesis that rho is equal to 0, R or rho is equal to 0, right? So that's the same p-value that we got when we did our correlation. So we're comfortable that this association is real. So this last box that we look at, that's going to give us a valuable insight into how we might actually apply this information. Notice that at one point here we have unstandardized coefficients. This first column is something called coefficients, and it has B in it. One of those values is 17.5, roughly, and the other value represents age, and it's 1.762. Let's call that 1.762. Let's call it 1.8 when we get into it in a second, just to make our little calculations a bit easier. So I'm going to get a piece of paper up here. Whoops. Let me get this out of the way. I'm going to get my piece of paper up here, and of course, I don't think my pen's still not working here. I don't know. I think I have to reboot in order to get this to work, but I'm not going to worry about that right now. I am going to draw a plot. Okay, X and Y axis. Here's my X axis. Here's my Y axis. Okay, Y axis. And I'm going to say to myself, okay, so now let's say I have a straight line. Right? I'm going to call this 0 here for X and 0 here for Y as it happens. Anybody remember what the formula for a straight line is? Bingo. Y is equal to mx plus b. I got that from Brian here in the lab. He's helping me with that. And I know Brian most recently took a math course, because math people describe it as mx plus b, where m is equal to the slope of the line and b is equal to the y-intercept. Well, how does that work? Well, what's happening here is that first of all, B is the y-intercept. And why do I know it's the y-intercept? Well, what if the value of x is equal to 0, right? If the value of x is equal to 0, you're over here, right? So if I plug in 0 for x, the slope times 0 is 0, so the value of y is just equal to b, which is the place where it crosses the y-axis, right? And m represents the slope. And if I look at that, what's the slope? The slope is the change in y over the change in x, right? So for every increase in x, you get a corresponding increase in y, and you get that by multiplying the slope, which is the same everywhere, right? Since it's a straight line, the slope is going to be the same all the way through the straight line, right? It's always the same slope, it's just a straight line. So that stays the same, but as x increases, y increases by that difference in our slope, change in y over change in x. So that represents the slope. This represents the y-intercept. Well, in statistics, we phrase it a little bit differently. We say y is equal to b or beta 0 plus beta 1 or b1 plus some error, epsilon or some error, e, right? So so what this describes is that's our y-intercept, except we put it up front there for whatever reason. It doesn't change anything. So beta 1 multiplies x. Beta 1's our slope. And then e is the difference between this line and where any particular value of x really lies. So in other words, if you have a person whose value for age and blood sugar is out here, well, that value of that spot, that person's blood sugar, y is equal to the y-intercept of the line plus the slope of the line times his age plus the error, and that distance between that line and that individual person is that error. Okay, so this formula, right? Y is equal to mx plus b, or in this form, y is equal to b1x plus b0, the slope, and the y-intercept times x. That formula describes this relationship. Well, now, if I want to see the relationship between age and blood sugar, I need to know what the values are for b0, the y-intercept, and for the slope, for this best fit line. This line that best fits all these values that are represented by all the subjects here. Okay, so what's the best way to describe this line? Well, I need those coefficients. Well, if I go back to my output, SPSS has given me those coefficients: 1.762 and 17.476. I'm going to call that 1.8 and 17.5. Right? So which is which? Well, this is the slope. 1.8 is the slope, and 17.5 is the y-intercept. So, make a long story short, probably too late, right? Y is equal to, and I'm just because I'm more comfortable, I'm going to put the slope first. It's going to be 1.8 times x plus the y-intercept, which was 17.5. Okay, now you might have noticed that when we looked at the significance of these two values, well, we have statistically significant value representing age, but not so much the y-intercept. You know, I'm not too worried about that because the y-intercept, it's kind of a funny thing. For instance, right here, at age is equal to 0, what's the blood sugar that's predicted by this y-intercept? Yeah, it doesn't, before someone's born, they probably don't have a y-intercept. They don't have a blood sugar before they're born, right? So it really doesn't make much sense. In fact, the y-intercept is more of a value that pins the line so you can draw it then it is something that gives you a lot of information about the relationship. However, the slope does give you a lot of information about the relationship. The slope suggests that for every 10-year increase in age, you get an 18-point increase in blood sugar. For a 20-year increase in age, you get 20 times 1.8. You get a 36 point, whatever it is, per deciliter increase in blood sugar. Okay, again, remember to take this with a grain of salt in terms of like its real applicability. Okay, I could rephrase this another way. Instead of y is equal to 1.8x plus 17.5, I could just really substitute what I'm really working with here. Blood sugar is equal to 1.8 times age, times a person's age, plus 17.5. I apologize for trying to do this with my finger while I'm holding down the keypad, the trackpad here. Okay, plus, excuse me, 17.5. Okay, this is our formula that predicts what blood sugar is based on age. So now I have a way to describe how blood sugar is related to a person's age, and maybe even use it predictively. That's why regression is so valuable. Now, I could say to myself, well, the regression, if I look at some other things that impact blood sugar, maybe I'll find that, there are other things that also impact blood sugar as well. But we can examine them separately. Or, on this coming Monday, we're going to come back to this. And we're going to see if we can't go beyond just the 65% or so of predictability that we have based on blood sugar. Remember, our R-square value told us it was roughly about 65% of the variability in blood sugar, that the change in blood sugar is attributable to a person's age. Maybe I can see what some other factors might be and combine them and create a formula that's even a stronger predictor as well. That's called multiple regression. You don't have to worry about that for today. So I'm going to go up here and I'm going to say to myself, let's go back to what we have here. So I could look at this a couple of ways. One way is I could pick a person out here. Okay, let me see if I can't get to my data again. Here it is. Here's my data. And I'm gonna pick one of these people out. And I'm gonna ask you, based on our formula, what would you predict that the blood sugar is for a 30-year-old person? Right? Don't look here, right? Because it's not gonna help you actually. Right? Just you guys tell me what, based on the formula we just created, what would you predict the blood sugar is for a 30-year-old person? I'll wait for an answer or two. Yep. Oh, I got somebody answer me really quick. Okay. Now, Betty, I'm going to do that now and see if Betty is right. Okay. So, 30-year-old person. So we have 30 times 1.8. Whoops. 30 times 1.8, age times the slope, is equal to 54. And I'll just put that into memory and clear it. And I'm going to add 17.5 to it. I could have actually done that right there and then. 17.5 plus, recall, well, no. Let me do this again. What did I say it was, 54? 58? I forget now. Let me do it again. 1.8 times, where is it? 30 is the age, yep. Equals that, plus 17.5. Okay, 71.5. So that's how Betty got that. She actually filled the value of x and put the value of x in there and actually calculated what the blood sugar would be. Well, what was the person's actual blood sugar? Let's see what it was. Was it 75? Somebody's telling me 75 here. It was 75. So our formula missed the right value by 3.5, right? We missed the right value by 3.5. That's the actual person's real blood sugar is 75. Okay, we missed it by 3.5. Well, that's our error. That's that little epsilon. That's the error in our formula. Anybody know what that's called? I think during the lecture, I think you heard the name for that, the error what we would have for this value, the error that we would have for this value, the error for this value, and so on and so forth. What are all these errors called? Anybody recall? How many of you guys fell asleep during the lecture? Tell the truth. It sounds like a few of you fell asleep during the lecture. That's called the residual. Those differences between the value that's predicted by the formula and the actual value, when you have actual values to compare it to, are called residuals. In fact, SPSS will help us calculate those residuals. I'm going to go back up here to Analyze. I'm going to go to a Regression and go to Linear. And we're going to go peek into a new spot here, this thing called Save. You haven't seen a button that says Save before. So I'm going to click into that. And SPSS will calculate for us predicted values, unstandardized predicted values, by the way. That means that it's not going to turn them into z-scores. It's just going to use them, the actual predicted values, just like we calculated a predicted value for blood sugar based on the age 30. It's going to calculate the real values based on the number, which is the age. If you wanted to know the values based on z-scores, how far from the z-scores, one z-scores for one variable versus the other, you would click standardized residuals. But we don't want those right now. Just right now, we're just looking at unstandardized residuals, unstandardized predicted values. Well, the difference between the actual value for the people that we have and the predicted values, in other words, what value that the formula gives us, is called the residuals. So I'm going to ask SPSS to calculate the residual as well. So I'm going to click Continue, and I'm going to click OK. And this time, interestingly enough, we got some extra statistics down here, residual statistics. Well, what's really interesting, also very interesting, is SPSS adds two more columns to our data view. And those two columns are the predicted values and the residual values. Okay, let's take a look at what we have here. Well, the age was 30. The person's actual blood sugar was 75. When we applied the formula, SPSS applied the formula, calculated, the predicted value became 34 rather, right? That's a little bit different than the one we did, but that's because I rounded it, right? Instead of 71.5, it came out to be 70.3, right? That's a rounding error, right? So it calculated the predicted value, and then it took 75, subtracted 70.33, and calculated that error, that residual that's left over. So all of these are residuals. Now, what were one of the things that came up during that video about these residuals? What did we want? What were we concerned about with these residuals? Well, one of the things that we were concerned about is we wanted these residuals to be normally distributed. Homoscedasticity, right? We wanted them to be normally distributed, okay, and to have roughly the same standard deviation for each group, each area of our table, that the variability for the lower end of these errors is the same as the variability of the upper end of our line for these kinds of errors. And we wanted this to be we wanted these values to be normally distributed. In other words, that these errors are random and they don't have some sort of pattern where there's greater variability at the top of the range and smaller variability at the bottom of the range, right? So we're kind of interested in how these are distributed. We'll talk about that later on. So we have our predictive values, our residual values, and so on. Okay, so now let's try another one of these. I'm not going to close that. I'll just minimize it. Let's go back to Blackboard. Let's see if I have another one that we can use. Okay, let's download this the SAV version of this database called Violent Crime. I'm going to download that, drop it on my desktop. Okay, and again, now I'm going to go back to SPSS and open it. And here's my violent crime database. I'm going to open it up. Okay. And here we go. What do I have here? Well, I have 51 pieces of data here. They're all 50 states, but I have 51 of them. Why is there 51 of them? Well, there's 51 of them because they included the District of Columbia as a state. And what we have here for a particular year, we have a number of numerical variables. The state name is a categorical variable. These are all numerical variables. The violent crime rate, the murder rate is probably a number per 100,000. Poverty rate, that may be a percentage. The high school graduation rate, the college graduation rate, the proportion of families that are single parent household, the unemployment rate in that state, and some sort of measure that predicts whether that's an urban or rural kind of setting, okay, metropolitan or rural. Okay, so let's see if we might find two of these variables where we might think that there might be an association. Okay, so let's think about this. Where might there be an association here? Okay, how about the relationship between the murder rate and, let's see, how about poverty? Let's look for an association between the murder rate and poverty in each of these 50 states. Well, what's the first place I might go? What's the first thing I might do to just examine it to see if there's a correlation, association, and if it's linear? Right? You guys agree with that? The graph, we want to do a scatter plot, right? Legacy dialogues. Okay, do a scatter plot. Okay, and okay, so it doesn't matter which I make the X and the Y, because right now I'm just looking for an association, but why not just to stay consistent? I'm going to guess that poverty would be the independent variable, and the violent crime rate might be, the murder rate might be the dependent variable. Okay, so I'm going to go ahead and click OK. See what this looks like. Okay, well, it's kind of hard to see. Uh-oh, what happened here? Anybody notice what happened here? Well, yeah, we can't tell here, can we? You see anything unusual here? Yeah, there's an outlier on here. And one of the things we learned in the lecture is that this happens to be a statistic that's very sensitive to outliers. What do you think that outlier might be? Well, that very well might be. Let's take a look. Okay, actually, there's a way for me to identify it, but properties window. I think I can get it to give me that. Okay, I don't want to look. I only have a few minutes left here. I don't want to kill it just playing around with this. Okay, so let's take a look at this data file. Where'd it go? Oh no, here we go. Let me go to SPSS again. Let me go to that white window. Crime, here we go. Okay, so let's look at DC. Well, DC, we have a poverty rate, 17.4%. Wow, look at this compared to all these other places. And this may have been over a short period of time. They may have had a spike in the murder rate in DC. Generally, it's pretty high, but this is really something weird. There might have been something unusual going on during this, maybe some period of gang violence, maybe a riot, something, whatever. But there's something that happened there that made this an outlier. So, you know what I'm thinking of doing? I'm thinking I'm going to delete that part of the data, and I'm going to take another look at it. Okay, so it's a little bit tricky for me to do this, right? I really should really have some justification for this. We're going to, it's a huge outlier. I'm going to go ahead and do that right now to see how I might proceed, how things might look otherwise. So I'm going to go to Legacy Dialogues again. I'm going to go to Scatter Dot. Let's see what this looks like now without that outlier in here. Okay, and here we go. Well, now it's starting to look a little bit more interesting, right? It looks like there's a linear correlation here, a positive linear correlation. As the poverty rate goes up, the murder rate also tends to go up state by state. Okay, let's draw a line there. Let's see what that line would look like. Okay, and here we are. Here's the line that we've drawn here. That's a best fit line. That's based on balancing the squares on the squares of the errors on this side versus squares of the errors on this side. It looks fairly randomly distributed above and below, maybe a little bit weird up here, but for the most part, these errors are kind of randomly. There's fewer and fewer that very far away, more of the errors that are closer, and so on. There's fewer values that are up at the high end here, but it doesn't look too bad so far, right? So let's take this and see, since it looks like we might have a pretty good linear relationship here, let's examine how good a linear relationship that is, what the Pearson's correlation value is, and whether or not it's statistically significant. Okay, whether or not that correlation is really due to chance. Can I reject the null hypothesis that the correlation coefficient for that relationship, rho, is equal to 0, and accept the alternative that rho is not equal to 0? So I'm going to go up to Analyze. I'm going to go to Regression, Linear. Okay. Actually, I got ahead of myself there, didn't I? I'm going to go to Analyze, Correlation. You really don't have to do this first, but I would like to. Correlation. And I'm going to take a look at the association, violent crime and murder rate, and let's see what it is. Pearson's correlation is what we're going to calculate. And if I calculate it, the association between violent crime and the murder rate gives us an R value positive. There's a positive association, positive number, 0.71. This is a very strong association. Once we got rid of that outlier, we could see this, we found this strong association. And is this association statistically significant? Can we say that may not be 0.71? Maybe it's a little bit different than 0.71. It just happens to be for this sample for this year. It's that strong an association. Excuse me? Oh my goodness, you're right. Excuse me. Analyze correlation. That probably one was right next to the other, and I took it by mistake. Murder rate and poverty. It's not going to be. It kind of surprised me that it was that good. And murder is a violent crime, so you would think that they'd be, oh yeah, this is more like it. It's a good association, 4.427, but it's not necessarily as strong as the one that we were looking at before, right? Which is almost a measure of the same two things to some degree. So at any rate, so our Pearson correlation is 0.427, and our significance, our p-value, the probability of being wrong if we reject the null hypothesis, is 0.002, less than 0.05. So we can reject the null hypothesis and say that the correlation coefficient is not 0, it's something other than 0. Okay, as it happens, we're predicting it's plus 0.427, it's positive, and that's the value. Now, in reality, the true population correlation coefficient might be 0.3 or it might be 0.5 and so on. But all this tells us is that it's not 0. And this is our estimate of what we think it is based on what our values are. Okay, so now I'm going to take this a step further and go to my to regression. Analyze, regression, and I'll go to linear regression. And now I'm going to put in my independent variables. I'm going to put in poverty rate and murder rate and actually calculate a series of values that'll give us our coefficients for our linear regression. So 0.427, that's just a repeat of what we've seen before. The probability of 0.002, we know it's a significant correlation. We can reject the null hypothesis that there is no correlation. And that r squared, 0.427 times 0.2427 comes out to be 0.18. 18% of the variability in the state's murder rate, in the different states' murder rates, is due to the poverty rate in that state. Okay, that tells us that 80% is due to something else. So the other factors. Maybe it's the prevalence of guns. Maybe it's a cultural thing. Maybe it's maybe it's areas where there's a lot of issues with robberies or drugs or gang violence and so on and so forth, right? But there's something else besides just the poverty rate that's driving this as well. Okay, there are other variables there that we could also look at, right? But for this one, 20% of the variability, 20% of what the murder rate is, the differences in the murder rates, can be attributed to this one variable, the poverty rate. Okay, and that's significant. It's real. That's a real impact. So what would be the formula that we would create to help us predict what the murder rate might be based on what the poverty rate is? And why might you want this? Well, you might want this because if you have a formula that can predict how poverty rate impacts the murder rate, well, then you could say to yourself, well, gee, if I reduce the poverty rate by this much, perhaps the impact of that will be to reduce the murder rate by this much as well, right? So why is that important? Because that then will help you understand what the response to interventions, to spending money to intervene in poverty rate and programs to reduce poverty rates and so on and so forth, how that might impact, among other things, the murder rate and violent crime rate and so on and so forth, right? So it'll help you understand which of these things that you could intervene in that would have the most impact. That's why regression is so valuable. So what would our formula look like? Formula would be as y is equal to 0.365 times the poverty rate plus 0.432 plus 0.432. That's our formula. Okay, and if you wanted to go up here, you could go to save and add the predicted values and residuals and see what those values are as well. And if you had a state that wasn't here, that was missed, say Puerto Rico, for instance, you might want to predict for Puerto Rico. If you know the population proportion for poverty in Puerto Rico, you might plug it into this formula to help you predict what you think the murder rate might be in Puerto Rico.